Good day, everyone, and welcome to another video with Special Maths Academy. In this video, we'll be discussing the 18th problem from the Special Maths Contest 2024. And of course, as you can see from the thumbnail, probably you already have a hint of how we're going to tackle this problem. So let's read it. How many ways can 2024 identical candies be shared among Pius, Williams, and Mesomachi? Okay, so I'm getting some candies so that Pius always gets the most and Williams always gets the least. No one receives zero candy and no two receive the same number of candies. So this is an important uh, counting question. And if we say let's denote the candies that Pius gets with P and denote the candies that Mesomachi gets with M and denote the candies so the number of candies that each of these people gets by the first, alphabet, the first letter of their names. And we know that Pius gets the most. Okay, so basically, and we know that Williams gets the least. And no two receive the same number of candies, okay? The same number of candies. So this inequality is strict. So basically, we have P strictly greater than N, strictly greater than W. Okay. So basically, we can interpret this into how many integer solutions are there. So this equation, so P plus N plus W equals to 2024, okay? And P is greater than M, greater than W, okay? So let's say the number of solutions to this. So how many solutions? How many integer solutions? Okay, I think this should be, if we should put, no one receives zero candy. Okay, so we should put zero here. So how many integer solutions does this have? So this is a simpler way to interpret this question. Okay. So let's say the answer to this question. So how many integer solutions to this? Let's say the answer to this is, let's just call it T. Okay. So now let's consider a similar question. Okay. So let me erase this up here. So if I consider a similar question, say, how many integer solutions are there to this? So we have P plus M plus W equals 2024. And P, we just have P greater than M greater than W. Sorry, we just have P, M, and W greater than 0. And we have that they're not pairwise equal. So P is not equal to M, M is not equal to W, and W is not equal to P. So they're not pairwise equal. So if I asked how many integer solutions are there to this new problem, this is going to be 3 factorial times T. So why is that? Because any solution, so any solution to this first case, so let me call this I and II. So any solution PMW, any solution to this first case, we can permute it. So we can rearrange it in 6 ways. So 3 factorial ways. And each of those permutations is a valid solution in the second case in II. So that's the reason why if we say the total number of solutions to the first case is T, then the total number of solutions to this second case is going to be 3 factorial times T, which is 6T. Now, why did I bring in the second case? Because the second case is actually much more easier to solve. Okay, so now let's break it down. So we're going to solve the second case. Okay, and how are we going to solve it? We're going to, we're going to consider cases where, so P is equals to M. Okay, P is equal to W and M is equal to W. And actually, for the The second counting problem, which I stated, each of these cases are equivalent. Okay, so they all give the same number of ways. So let's just pick one and find out the number of ways. So if P is equals to M, so let's just say we want to find number of solutions to M plus W equals to 2024, and M and W, this is M, and W are both greater than 0. Okay. So if we want to find the number of solutions to this, we can look at it this way. So we have 2M plus W equals to 2024. Okay. And we have, so let me call this, let me denote this by sets. So let the set of solutions where P is equals to M, let me just call it SPM. The set of solutions where P is equals to W, let me call it SWP. The set of solutions where M is equals to W, let's call it SMW. Okay. So now, if we have 2M plus W equals 2024, we can now make W, sorry, the formula. So W is equals to 2024 minus 2M. We can factor out the 2. So 2 into 1012 minus M. Okay. So how many solutions do we have here? Okay. So recall that W has to be greater than 0. So basically, M can take the values from 1 to 1011. Okay. So M is free to take the values from 1 to 1011. So what does that mean? It means that, so let me erase some of these things here. So it means that the cardinality of the set SPM is equals to 1011. And in fact, let me just put it this way, because remember I said they are all uh, equivalent. So the cardinality of SPM is equal to the cardinality of SWP. So I'm bringing instead because I'm going to use inclusion exclusion principle. Okay. So now, what else do we need? We need the intersection of the three sets. Okay. So basically, uh we want to find the set of solutions where at least some form of equality holds. Okay. So basically, we want to find this union SWP union SMW. So we want to find this. Okay. So by inclusion exclusion principle, this is equals to SPM plus SWP plus SMW minus SPM intersects SWP minus SWP intersect SNW minus SNW intersect SPN plus SPM intersect SWP intersect, so let me erase this, intersect SMW. Okay. So this is what we want to find. Okay. So we want to find this first of all. And we'll soon see why uh we can find this. So next, let me erase this. Okay, so next we want to find the intersection of two sets. So now the intersection of any of the two sets, so SPM, so let's say SPM intersect SWP. Okay. The intersection of any two sets gives rise to one case that P is equals to M is equals to W. So any two sets you pick and you like consider their intersection, the condition is always going to be P equals to M equals to W. So basically we have P plus P plus P being equals to 2024. P is greater than 0. Okay. So here, what do we have? We have that 3P is equals to 2024. I want to find integer solutions. But 3 does not divide 2024. So what do we have? 3 will go into 2024. So we have 6, 7, 4, remainder 2. Okay? So we see that it's not possible that there are no integer solutions here. So it means here we have that. So let me use a red. We have this is equals to 0, this is equals to 0, this is equals to 0, and the intersection of all three of them. So recall that even if you take the intersection of all three of them, you're still talking about the case P equals to M equals to W. So this is also equals to 0. Okay. So let's me erase this and let's go back to the problem. So it means that we can now find the union. So this union SWP union SMW. So this is equals to, so we have 3 times 1001, 1011 rather, because these first 3 terms are all equal. And then we have minus 0, 0, 0, 0. Okay, so basically this just equals 3 times 1011. Okay. So basically we've counted the possibilities where at least 2 people get equal candies. Okay. So where at least 2 people get equal candies. So basically we're calculating the complement. Okay, so now another thing we want to calculate is the total number of ways. So let's just call it U. So total number of ways that we could share these candies. So if we're not looking at um any condition of how they receive it. So all we just want to find is total number of ways of sharing these candies. Okay. So that is just equivalent to just this. Okay, so no condition given. So let's call it U. Okay. So the total number of ways of distributing these candies where P is equals to M is equals to M, where P, M, and W are greater than 0 rather, and P plus M plus W is equals to 2024. So we can consider, we can put 2024 candies on a row, and then we have 2023 spaces in between the candies. Okay, so 2023 spaces in between the candies. So let me just use maybe, let me try to make my candies. Let me draw my candies better way. So let me scroll down a bit. So this is another counting technique that is important. So let's say we put the candies, 2024 candies in a row. And then we now consider the spaces. So 2024. So candy 1, candy 2, candy 3, candy 2023, candy 2024. Okay. And then we consider the spaces between these candies. How many spaces are there? Okay, so there'll be 2023 spaces, space 1, space 2, up to 2023. Okay. So now if we now say we want to divide these candies into just 3, right? We want to find P plus M plus W equals 24, the number of ways we can, partition that. We can select any of these 2 spaces. So we can select 2 spaces out of this, and that will map to one so one possible solution in the set of solutions P plus N plus W equals 2024. So for instance, if we select the two spaces, the first two spaces, that will map to 1 plus 1 plus 2022. Okay. So this we're also considering a way of dividing the candies. So we have 2023 spaces. I want to select two. So that's 2023 combination 2. Okay. So it means the the cardinality of the universal set is equal to 2023 combination 2. So I can just do 2023 combination 2. That's equal to 2023 times 2022 divided by 2. Okay, so that's equals to 2023 times 1011. Okay, so the cardinality of the universal set, so where we're just sharing the candies, we don't care how some people receive more than others and others. The number of ways that can be done is 2023 times 1011. Okay, so let's write that somewhere. So I'll erase this. I'll erase this and I'll erase this and I'll just write this is equals to 2023 times 1011. Okay. So now, if you want to count the complement, so recall we counted the conditions where at least there is one, two people get the same number of candies. So now I want to count the complement. So we subtract this from the total. Okay. So basically 60. So let's come back to 60. Let me erase this. So 60 is equal to, so the total number of ways of sharing the candies minus the total number of ways of sharing the candies where at least two people receive equal or the same amount of candies. Okay. So we're counting this by, counting the complement. So this is equals to 60. So 60 is equals to 2023 times 1011 minus 3 times 1011. Okay. And so this is equal to 2020 times 1011. Okay. So it means T, so we can divide by 6. T is equal to, so 2020 times 1011 divided by 6. And this is equals to, so 2 will go into this 1010. And 3 will go into this. So to be 3, 3, 7. Okay. And so we have 1010 times 337. So that's option D. Okay, so this is our answer. And this is, a very good problem. This is a problem that shows a very good application of inclusion exclusion principle. So inclusion exclusion principle is what was applied. So basically this formula here, so this inclusion exclusion principle, I'll just write that for readers who want to, people who want to do more reading. So inclusion exclusion principle in counting. Okay. So inclusion exclusion principle in counting. And that'll be all for this video. I hope you enjoyed it and see you in the next video. Goodbye.